So get off my thread. Really, we just want to move stuff off the current thread onto something onto the background thread. And so obviously we're going to talk about why we might want to do that. Then we're going to look at how we might do that, and then we're going to have some final guidelines and questions to wrap everything up. So, yes, why do we need to move work off the current thread? Well, fundamentally, then lots of us live in and work in environments where there is some thread that is dedicated to processing external events. Now, that might be a GUI, where you have a message handling thread. The OS is passing you messages, or the windowing environment is passing you messages, and they have to be handled on that thread. Or you might be running some form of client-server or network application where the network handling is running on a specific thread. So you have the socket notifications come in. Yes, there's some new data on the socket, so then I'm going to process that. I'm going to respond to that, and then I will go back and call select as appropriate. And then whatever the reason why you have to have your events handled on a specific thread, if you then perform extensive processing in response to those events, then that then blocks that thread. It prevents you from handling any further messages. So we want to get our work off that thread. So because delaying these responses to external events can have consequences that are disastrous. I mean, they might be unpleasant for our users. They might actually have genuine things that are actually going to cost things money, but there are going to be consequences. Now, if you're running a Windows application and you don't respond to your events, then you're going to grey out the entire application window. And users are going to notice that, they're going to complain and potentially not use your application. The application window won't respond, you will get support problems, and then people might, yes, they will switch to your competitors if the competitors don't have that problem. If you're running a web server and the web browser sends its request and you don't respond, then at some point the web browser is going to give up. It will give you a timed out notification. Your user won't see a nice, your nice web application. They'll see a nasty, error message from Firefox or Chrome. And if you're not running within a browser framework, but you are running other network applications, then most systems will going to have a timeout on an operation. And if you don't get a response within the timeout, then they're going to do something else. That might be they treat it as a failed request and cancel it. Or it might be that there is that the application repeats the request, and so now your messages are doubled up. But any which way it happens, if you don't respond to your events in a timely fashion, there are undesirable consequences. And so we want to move that work off the event handling thread. And we don't just need to move the work. We need to prevent any blocking on our event handling threads. It's all very well saying our event handler is going to spawn some background task. But if we then wait for the background task to finish, even if we've done some other processing in between, then that wait there throws out all the benefit that we've gained from actually doing that work on the background thread, because the event handler is still blocked and still can't process events. So we need to prevent that blocking. So I just want to have a quick aside here about preventing blocking. and say, well, in lots of cases, then short-term blocking, like locking a mutex, is okay if we know that other thread. If you're locking a mutex, if the other threads are not going to hold the mutex lock for a very long at all, then it's just a little mutex lock around a Boolean flag, for example, and the other thread locks the mutex, sets the flag, unlocks the mutex. If that's the case, then in many cases that might be acceptable. The worst case blocking time is really short, and there isn't a problem. And so particularly in user interface based scenarios, then what we really want is not to be waiting for a lengthy period of time. We're not waiting for a lengthy task to run. And so that's what we mean by non-blocking. But in other cases, it's really, really important that we genuinely do not block. We mean obstruction-free. If you suspend all the other threads, but the event handling thread will complete its task. And that means that you can't use things like mutexes, because if another thread has locked the mutex, then your event handling thread now will have to wait for it. And if the other threads are all suspended, then it will wait forever. And you need to then be using lock-free implementations of just about everything around your event handling thread. That means lock-free allocators, it means message queues that are lock-free, and everything that goes with that. So in some cases, you really, really need that. And in other cases, we just mean no long-term waiting, no waiting with an indefinite timeout, but short-term mutex blocks is okay. So just bear in mind, if you're thinking about this in your application, which of those cases do you fit in? Have you got a hard real-time performance critical scenario where you need obstruction-free, or is it just the long-term blocking that you need to avoid? So that was a quick detour into why we might move work off the thread, but obviously the meat of this is how are we going to do it? So there's a myriad of possible ways. In some ways, the simplest possible thing we could do is we could just say, well, let's spawn a new thread for each event handler. Every time you want an event, spawn a new thread, then it will do its task, then it will finish. It's not going to do that. Alternatively, you can have a dedicated background thread, and you can pass data to that by some prearranged mechanism. Whether that is there is a block of shared memory and you lock a mutex and stick some data in there and then unlock the mutex. Or is it, on the other hand, that there is your background thread is having a message queue, and you are that is obviously a special case of a shared data memory. It's a very focused message queue, and you pass messages onto it. And so there are cases when such a dedicated background thread might be useful. Alternatively, you might not have a dedicated thread, but have a thread pool. And so when your event comes in, your event handler needs to deal with it. It knows there's a lengthy task to do. It submits that task to the thread pool. And then finally, there might be not just a generic thread pool, but various special purpose executors that you might be able to use. If it's a number crunching task, you might delegate it to a GPU executor, for example. If your system has a GPU that you can use for that purpose. So again, the common factor of all these things is that we are moving the work off the current thread so that the event handling thread can get back to doing what's really important, which is handling the events from the external systems, so that the thing, whatever it is that you're interacting with, whether it's the operating system, the UI, or network clients, they are seeing timely responses, and making sure that you are processing the events as they come in. So if you are spawning new threads, there's loads of ways you can do it. Standard ways, we've got standard thread, we've got in C++20, we've got standard JThread, we've got standard async. And actually, there's a typo there. If you pass standard launch sync, then it really isn't a thread. But if you standard launch async for starting a new thread, and then platform-specific APIs. That you could use the Windows begin thread or create thread APIs. You could use POSIX pthread create or anything again relating to whatever platform you're happening to be working on. But they all share the same fundamental problem, is that you are spawning a new thread, and if you detach the thread, then you now have there's nothing there that's going to directly relate to when it's going to finish, how long it's going to be running. Your event handler now has nothing to tie it back unless you put something specific in there. On the other hand, if you try and join the thread, then somehow you've got to keep the thread handler around and know when to join. From that perspective, then standard thread and standard JThread, they don't give you any, there's no difference there really. A JThread just provides a slightly nicer interface. So if you're going to join with it, then you construct your JThread to process the events, and then you push your thread back onto this list of pending threads. Threads I've started, but I need to join with at some point. But the fundamental issue around that is, at what point are you going to join? How are you going to know when to join? Because there is no reasonable way to test if any of the pending entries in pending threads can be joined. So, if your event handler thread definitely can't, then at any point it can't call join on any of your threads unless you've put something explicit, an external event that you're then passing back to say, yes, this thread has now finished. And but on the other hand, if you leave it to the end of your application, then you've just got all these vast numbers of threads, because there's going to be, presuming your application is long running and it's going to handle a lot of events in its lifetime, then spawning all these threads, then they're just going to accumulate, and eventually you'll run out of system resources. So you really don't know. There's a lot of danger there. What do you do with these pending threads? How do we gather them up? How do we join with them? So if we use async, then it's a little bit better, because we can actually check to see whether the futures are ready. So again, on our handle event task, we can do our launch our new thread with standard async launch async, and we can put that future on our pending threads list, which they're now not just raw thread handles, they're standard futures. And so on that front, it's exactly the same. But on the other hand, we now have the ability to check whether these are ready. We can iterate through our pending threads list, and we can poll each future to see if it's ready. And if it is, then we can erase it from the list. Now, obviously, if you accumulate large numbers of events, and then you have large numbers of threads, and so yes, you can do this polling, but somebody's got to do it, and it's going to be a time-consuming thing, because if you end up with hundreds of features there, checking them all, well, how often are you going to check them, and how it's going to take a while to scan through them all to see if they've all done, and if most of the time they're not going to be done, then you're just wasting a lot of time checking. So what you really want is some form of notification, and we just don't have that with these facilities. Yes. And so this is still nasty. If you have a lot of events, you still end up spawning a lot of threads, and the list just gets large. So fundamentally, I wanted to introduce it because it's something that in some senses seems simple, getting the work off my thread, but really spawning a new thread for every task is fundamentally a bad idea. A dedicated thread, on the other hand, can be a reasonable idea. So the workflow that you might go through is that at some point you're going to start your dedicated thread. This might be in response to an event. We have an event that somebody clicks a button that says we're going to start this operation, and then there will be things to follow. Then now a new window in your application, it's got new events to handle, new things it's going to do. And so we create our dedicated thread. Once the thread is created, at some point your event handler is going to receive an event. And rather than processing itself, it then reposts that event as a message to the dedicated thread, either directly using a message queue for that form of structure, or alternatively by locking a mutex and modifying some shared data or something like that. But whichever way it does it, somehow it passes the data that the event has happened onto the background thread, and the event handler is then done. It can return to its caller ready to receive a new event. And then that little cycle, steps 2, 3, 4, is then going to repeat. But the crucial part then is that while that is repeating, at some point later, hopefully not too much later, the dedicated thread is going to receive this message, and that in turn is going to process it. Now at this point, then, provided that overall our system does have enough computing resources to deal with the background processing and the event handling, then the time it takes to process it is so much less of an issue. Obviously, we want things to be processed as fast as possible, but we don't need to complete our processing in any particular time frame. And so, yes, you might need to somehow pass the response back from your dedicated thread to the event handler, and that is something that we are going to look at later. But from this point, we're just looking at how we get the data to our dedicated thread. So we post our message and sometimes process it. And then when it's done its little bit of processing for that message, it's then going to wait for more messages to process. And then eventually, when it's done, then the dedicated thread is going to be destroyed at the end. Maybe you close the window, maybe you finish the long-running operation that it's done, but whatever, eventually it will come to a natural conclusion and we will destroy the thread. So there are some downsides to this. It's not an outright bad idea, like having just spawning new threads every other minute, or every other millisecond, is quite possibly likely if you've got a lot of incoming messages. So the first downside is that it is a long-lived thread, and it's going to consume resources, both in terms of memory, in terms of processing, and it consumes those resources even when it's not actually doing any. There's no current events coming in to process it. It's still going to sit there. The memory for the thread stack and the thread local data structures and whatever else is just fixed and allocated, and it's going to sit there. And so that might be an issue. It might not. You might have loads of memory, and the number of threads in your application is small enough that you don't have to worry about running out of thread or thread handles. You don't, and that sort of thing. And so you might have to worry, but it's there. There is a persistent cost for the whole time that the dedicated thread exists. And then the handling of the event is now disconnected from the event itself. And so depending on how easily and how quickly the background thread checks its message queue and how timely it is, then you might find that the time between the incoming messages being processed there might be several milliseconds between the incoming event being processed, being received by the event handling thread, and then being processed by the dedicated background thread. And depending on your application, that might be an issue. But it's something that you need to be aware of, just because there is going to be that disconnect. And then by its very nature, we've got a dedicated single thread, and so therefore there is no parallel processing. It's all very well if you've got a nice hefty server with 128 core CPU, but you've got one event thread and then one dedicated processing thread, then that's not going to do you any good. And the other 126 threads are just left to the OS to decide what to do with. So you need to, if you're wanting parallel processing, you need to do more than just have a dedicated thread. It's not all downside. There are upsides. The first of which is a nice and very simple upside, is that the events are handled in the same order as they arrive at the initial event handler. The event comes in, the event handler puts it on the message queue, and then the second event comes in, the event handler puts that on the back of the message queue. The message queue now has two events and two messages, and they get processed in order by your background thread. This can be of huge benefit from the point of view of analyzing how your system is going to respond. Having events processed out of order has a very large scope for making things go wrong. Even little things. So I'm sure we've all experienced applications where you click on a button and nothing happens, and then you click on a button and the second button, or maybe the same button again, then the window gets popped up, and then your button click now gets redirected to the new window, and even though the window wasn't shown at the point when you clicked. Then so the handling, the ordering of the window display and the event and the handling of the button event is not maintained, and so you need to be make sure that sort of thing is happening in order. And you wouldn't want to be typing and find that the letters come out in a different order so you pressed your keys. They need to be processed in order in many applications. Otherwise, everything just gets confused. And so having a single dedicated thread, by its very nature, tends to enforce that. And then if we say that the dedicated thread only communicates with the outside world via the messages, so it receives messages from our event thread and then potentially passes messages out again, then it becomes very, very easy to design and test comparatively, in the sense that our whole application is multi-threaded, but this is a single thread with a message queue. So you can design it the same way you would anything else that's got a single thread. You can use state machines, and so your incoming messages trigger state transitions if you find that is an easy way of structuring things. Alternatively, you don't have to use a state machine, but you can build your little bit parts of the system, and you can fire in a sequence of messages and then check that the appropriate side effects actually from the thread itself in terms of whatever other processing it does, and then any other messages that it sends out, and verify that those are all correct. And in the whole system, your test can now consist of just the single one dedicated thread and this message queue, which you can preload with messages from your tests. So that does make it substantially easier. And then if you have, when you're closing your application, somebody closes the window, the web browser closes the connection or whatever, then if you have outstanding tasks, then it's dead easy to clean them all up. You just shut down the thread and abandon anything left in the message queue. So that can be a very easy thing, from the point of view of cancelling an incomplete task. But if dedicated processing isn't an ideal fit for our application, then an alternative is to use a thread pool. And so we don't have just one thread, we have many. And then the system processing of the events goes very much the same. You create a thread pool, you receive an event, you post as a task to the thread pool, whereas with a dedicated thread, then we would tend to have some form of message, and then the thread itself would know what to do with that message. When you're posting through a thread pool, the thread pool doesn't know what to do with anything. So instead of giving it a message, you give it a task. This is what I want you to do. Here, not only here is the data, but here is the function that I'm actually going to run. And then the event handler returns back, ready for receiving new events. So the structure here is very much the same, but not just the dedicated thread, but one of the threads from the thread pool will pick up our task. We don't know which one. And that thread will then wait for a new task. Of course, if we've got a thread pool, the reason we've got a thread pool is because it's got multiple threads. And so now the event handlers might be posting multiple tasks, and then they might all be picked up and now be running simultaneously. And then, of course, eventually the thread pool is going to be destroyed. So it's a very similar overview, but with some crucial differences. Now, obviously, the upside to thread pools is that our tasks are small. Now, you've written your tiny little tasks and you make them self-contained. This is what I want to do. Here is some little bit of data I got from the event. This is the processing I want to do. This is the state of the rest of the application that I'm going to work in. And so you can design your task and test it, and it's quite straightforward. And the natural aspect of thread pools is that the number of threads is scalable. You're running on a 4-core machine, and mostly you're going to run approximately 4 threads. You might run a bit more or a bit less, just depending what else is going on in your system. But you're going to be approximately that. If you start moving to 128 cores or a serious server with 1024 cores, then you scale up the number of threads in your thread pool, and it just naturally expands to divide the work up between with the available hardware. And then the threads are not dedicated. It's just a generic thread pool. You can now use this, share it with the rest of your application. And so every part of your application can post tasks onto the thread pool, and the thread pool deals with allocating those tasks to threads and making sure that everything runs. See, they're not all upsides. There's downsides to thread pools. And the first of which is that your tasks are run in an arbitrary order as they are picked up by the thread pool. There is nothing nothing inherent in the way that thread pools work that are going to specify that your tasks run in a defined order unless you put in something specific mechanism to enforce that. So you post 3 messages, post 3 tasks on your thread pool task queue, and then they might all be picked up, all 3, by separate threads. Alternatively, you might find that one of them goes to a thread that's currently busy, and the second and third get picked up by another thread, and they get run first. And then the first one gets delayed. So there's a lot of scope for how the ordering, and if you and it's a general thing, if you just submit tasks to the thread pool without anything specific in there to constrain ordering, they will be run in an arbitrary order. Our event handling is still disconnected from the event. Fundamentally, there's not a lot we can do about this as a problem, because that's by getting it off the main event thread onto the background thread, we've enforced that disconnect. And not only are tasks run in arbitrary order, but if our thread pool is going to live up to its name and have multiple threads, then our tasks may indeed run concurrently. And that means that if they operate on any form of shared state, we need to verify that their interactions actually work as intended. So our testing, though we might have thought that our testing could be done on purely simple individual tasks, we do have to make sure that if those tasks interact with shared state, then their synchronization with that shared state is done correctly, and think about how they might interact with each other if they are indeed run concurrently. And then there's a very specific thing about thread pools. If you're sharing your thread pool with other parts of the application, then if another part of the application submits a whole bunch of tasks onto the thread pool, then the event handling tasks might be arbitrarily delayed because they end up further back in the queue. Somebody's just submitted 100 tasks, and you've only got 4 threads. It's going to take a while for the thread pool to process them all. So that can be a very real issue, whereas at least if you have a dedicated thread, then if you have a dedicated thread, then the OS will preempt your threads, and if you have other threads in the application running, but generally your thread will keep processing in a relatively timely fashion, and it won't have big pauses where other threads in the application suddenly, well, I'm just going to run for 3 seconds, and that thread's going to be paused. They tend to be incremental interleaving rather than big pauses. And yes, it is a strong recommendation that you want to minimize the interactions between your tasks and make sure that they are as self-contained as possible. Depending on your application structure, that might be harder or easier to do, but that is the strong recommendation, is that you do indeed make sure that your tasks are independent. And again, if you're sharing your thread pool with other parts of the application, then it becomes very hard to cancel just your tasks. If you've got a dedicated thread, you can shut down the thread and destroy everything in the message queue. If you're sharing your thread pool with the rest of the application, you don't necessarily want to shut down the whole thread pool and everything in the application. So cancelling just the tasks associated with a particular GUI window or a particular client connection can be actually quite hard. You need to think about how to do that, and that sort of thing. And so that can be an important thing. So I think that the biggest downside from thread pools is the unpredictable ordering. But we can solve that with continuations. The idea is fundamentally that if task B is a continuation of task A, it cannot run concurrently. The thread pool will not even attempt to run it. So if you submit both tasks A and B into the thread pool and mark that task B is a continuation of task A, then even if you have 15 idle threads when task A is running, none of the other threads are going to pick up task B until task A is finished. And so now we have our ordering that guarantees that things happen in the right order. And so we can enforce that then on our, from our event queue. We can keep track of what the last task that we submitted to the thread pool was, and then we can chain our event handler as a continuation of that task rather than submitting a fresh task every time. And obviously, if we haven't got an existing task, then we can submit a fresh one. If you know that the events are unrelated, then obviously you don't have to. You can submit things as continuations where it matters and have them as not continuations where they're not, based on your appropriate business logic. But fundamentally, we can do with that this way. If you did this for all your events, then you are losing some of the benefit of the thread pool because you are now putting an ordering on your tasks. And that then only provides a benefit if you're sharing the thread pool with the rest of your system. So, upsides. Is the big upside, our events are now handled in the order they arrive. And they are not handled concurrently. Now, these are obviously tightly related. If they were handled concurrently, they would not be strictly in order. But both of them are important because, again, those tasks that are handled as continuations now are essentially single-threaded. And so we don't have to worry about synchronization issues. Okay. But we've eliminated the concurrency of our processing, so we can delay subsequent event processing. So that is clearly a downside, but it still doesn't fix our other problems. We still have to deal with cancellation. We still need to. We still have that disconnect from the event. From the event itself and then the processing. So continuations are good for some aspects, but they don't solve all our problems. So one of the big outstanding problems, which people are asking questions about as well, is how do we deal with cancellation? And you might need to cancel tasks submitted. So you've submitted a task, somebody clicks download that big file or process that huge image or any other sort of long-running task, and then they click cancel. I don't want to do that anymore. So somehow you need to stop the tasks that have been submitted that in response to earlier events. So particularly if you've got long-running tasks, but also even if there were a series of short-running tasks, but actually now we just close the whole application, we want everything to tidy up and go away. So we need to avoid having dangling tasks where the task itself keeps running even though we no longer have any need for it. We want it to go away. So we want some means of cancelling tasks in a nice, timely fashion. If you've got a nice, shiny C++20 compiler, then I would recommend standard stop token is the tool for the job. You pass your stop token to every task that might need to be cancelled, and then that task can then use it. It can use it with condition variables, and you can use it in association with a stop callback to handle blocking system calls and anything else, provided that your API does provide some means of cancelling those tasks. So if you have a blocking IO call, but you have a cancel IO function of some description that you can call to interrupt that blocking IO, you can use that with a stop callback in conjunction with your stop token. And then when the cancel request comes through, your cancelling function will be invoked and the task interrupted. You keep the stop source in the event handler, and then you call request stop when the appropriate set of tasks need to be stopped. So you can keep multiple stop sources around. If your events and tasks divvy up into little portions, well, there's this set of tasks that relate to downloading that file. There's this set of tasks that relate to animating that window. And then when somebody clicks the cancel button for the file, or they click on stop on the animation, then you can trigger the appropriate source and call the appropriate request stop function to make sure that the appropriate things get stopped. So you need to be aware that just because you ask the task to stop doesn't mean it stops immediately. No, the stop token mechanism is purely cooperative, and generally that's what you want. Even if you don't have stop token, you use something else that you've built yourself or some other facility that you're using from the libraries you've got, then most things are not instantaneous. There is some form of cooperation and delay, and so you need to actually then ensure that the tasks have been stopped before you try and clean up any data they might be operating on. The simplest way to do that is just to keep a count of how many tasks you've got. You have an unsigned count, a number of pending tasks, and when you handle events, you increase the number of tasks because you're submitting one to the queue. Then when it is done, then whether it was completed or whether it was interrupted, then it decreases the number of pending tasks and notifies. So if I was the last task, assuming when it hits 0, I was the last task. Please be awaited. Take note, this is using the new C++20 waiting feature for the Atomic. Obviously, if you don't have a C++20 compiler, then you can use something else. So on Linux, you might use a Futex, or on Windows, you might use wait on address. Both of these are fundamental things that are built underneath the atomic waiting. Or you might use something higher level. You might use a condition variable, or you might use a Windows event or something. But either way round, you can decrement the count and then notify if it is 0. When you're trying to cancel things, you just you cancel the tasks. I should say request stop, not stop token. And then when you're waiting for them to clean up, then make sure, obviously, you don't do this in an event handler. You should not be doing a blocking wait in an event handler. Somebody's going to wait for the tasks, and you read the count. If it's not 0, you wait for it to be notified, and then you loop round again. And this will only this will be a blocking wait. It will only loop round when either it's been notified, which will be when the count was 0, because that's what we did with our event handler, or when there's a spurious wait, and the OS will look at the count and say, well, it has changed, so maybe you want to check it again. So that's why we put the while loop there. But fundamentally, this is a blocking wait, and the OS will actually suspend your thread for most of the processing here. So you really don't want to do this in your event handler. But you can do it, say, in the destructor for a class. You created done all the processing. Then you finished everything. So you're shutting down. You stick this wait for tasks in the destructor, and that makes sure that all the tasks are drained through from the thread pool that relate to this particular aspect before we move on. So what about progress updates? How does the background tasks in our thread pool or a dedicated thread, how do they talk back to our event handler? Now, maybe there's got a response they've got to send back over the network. Maybe there's a change to the UI that needs to happen, even if it's just literally moving the progress bar. Now, fundamentally, we might need to update the event thread with new information from the background threads. It might be progress updates, it might be other updates in the UI. We might need to change the window. We might need to stick red wiggly lines under misspelled words, or other draw a graph of the relative frequencies of different data items that have been being calculated in the background thread. The task is finished. Here is the data. Please draw it. Whatever. Somehow we've got all these information coming back to the UI. Might be some I/O that needs to happen, and of course it has to happen on the I/O loop if that's the way your application is built. But either way, somehow you need to trigger some form of event on the event thread, and usually it has to be the same sort of thing that the event thread is waiting for. If your event thread is a GUI thread waiting for messages from the windowing system, then you need to send it a Windows system message, probably a custom message type, but it acknowledged, registered with the windowing system. If it's an I/O loop, then you might be able to use something like eventfd to give you a file handle, which you can use to trigger. Here is an event on my file handle, and then your event thread can say, that's an event on my special event file handle, which therefore I know means that I've got some message coming from my background thread. Or there might be other similar mechanisms for other platforms. But fundamentally, you're probably going to have to package the message from the background thread as something that the event thread is going to look for without interrupting its normal processing flow. It might be that the only information that the message tells it is, look in this message queue over here, but which can then be a custom application-specific message queue. But you need to break it out of its normal message loop and say, actually, there's something coming in from the background thread. So then, your background thread, it's got some progress. I'm 99% done, and I'm going to post a progress event onto the event loop, onto the event queue that the event loop is processing. And then in your event loop, you receive a specific progress event, and which you can then use to update the UI with the new progress level, or whatever else it is that needs to happen, that is actually being affected. So, coroutines. Lots of people love coroutines and they like to use them for this sort of task. But they are not a magical solution. You can't just say, yeah, let's use coroutines. It's all marvelous, problem solved. No. But they can make your code simpler looking. And aside from the coroutine library itself, your code can actually be, it's not just simpler looking, it's simpler, easier to maintain. Now, if your coroutine library is well written, then your code can be simpler. When you handle the event, you can call your coroutine library and say, schedule on the thread pool this coroutine that's going to process the details from this event. In our processing function, then, which is it's a task for the coroutine, which the coroutine library you're using knows about, then you can just you can say step 1, and wait for step 1. Then I'm going to schedule an update on the GUI thread to say that progress has happened. I'm going to schedule wait for step 2 to complete, and then schedule again something on the GUI thread for progress to happen. And all this is very simple, straightforward lines of code. This processing can be a long-running task, but every time there's a co-await there, then it schedules it as a continuation, and so it allows other things from your application to interleave on the thread pool. But it's simple from the point of view of you writing the code. Everything looks nice and sequential. You can see clearly that step 1 happens before step 2, that there's no update to the progress in between, but your code doesn't have to deal with the complexities of scheduling continuations and writing it in a continuation style and making sure that all the data stays alive for all the continuations, because your coroutine library, along with the C++20 coroutine infrastructure, deals with all that for you. Obviously, you need a coroutine library. C++20 doesn't provide us with one. You might want to use something like the CppCon coroutine library, and or you might want to write your own. But either way, you can simplify the end user code, the application level code, with coroutines. It can make the overall application level code look a lot simpler, whilst simultaneously using a thread pool under the hood and dealing with the interactions and the continuations, and making sure that then that integrates nicely with other parts of the application, and seamlessly scheduling tasks that need to run back on the GUI thread get seamlessly scheduled there. The library is abstracting, posting those application-specific, the messages, the progress event message that was specific to the event loop, is then seamlessly wrapped in our schedule on the GUI thread function. We don't need to worry about the details. That's just wrapped up in the library. So you can write this. It doesn't have to be coroutines. You can write this sort of infrastructure with anything, but they certainly do provide one way of making things look simple. So some final guidelines. Obviously, the first one is that the reason we're doing this is we want our threads to be responsive. So if you have a time-consuming task, you really, really must not run it on the thread that needs to be responsive. And that includes waiting for tasks to finish once you've submitted them to your background threads, because waiting blocks for an unspecified length of time and therefore interrupts your ability to deal with messages and be responsive to messages and events coming in from outside. If you have a very long-running task, then a dedicated thread really makes sense, because it's there, it can just process its long-running task in sequence, and it can periodically check for new messages or send things back to the event, but it doesn't have to worry about things being out of order or interleaved with other tasks. But if the individual parts can be small, then you might want to use a thread pool, and then you can submit lots of tiny tasks to your thread pool, and that scales nicely as your hardware scales, gets more cores, then your application will scale if you've used something like a thread pool. If you need to cancel, then stock token is a really nice API and it's really flexible. If you don't have it with your compiler, then have a look at how it works and see whether you can construct something similar for your system that uses the libraries you do have available. Obviously, we don't want dangling pointers, so we need to make sure that our tasks are finished before we try and destroy any data they reference. The simplest way to do that is just to count how many tasks there are. You could do that counting with a reference count like in shared pointer, But that's a very simple thing, is count tasks, and then you can clear up when everything's done. And make sure you know whether you're in the scenario where you really, really, really need to avoid all blocking, you need genuine lock-free, obstruction-free code, or whether you just need short-lived locks and you have as long as it's done in a reasonable, timely fashion, and we know that our locks are only held for a short period of time, so that's okay, then that's wanted. Whereas if you need the hard guarantee that this code is obstruction-free, then that makes things a lot more complicated, and you really need to pay attention to all aspects of anything that interacts with that thread. And so that is the end of my talk. So time for questions. Now, I believe that I would like to think that I've dealt with the questions we've got. So I'm not sure whether any threads we've got out here. Are there any good examples of cancelling a thread or killing malfunctioning threads? No. I mean, if you have a malfunctioning thread that is spinning in the background, then you could kill it with something like hard and brutal, like Windows terminate thread. But I would not recommend it, because if you do, then you do not know what state that thread has left the rest of your application. If you're wanting to have brute force killing in your system, then I would recommend you don't use threads for your concurrency, you use processes. And then you can have a watchdog process that kills and restarts individual processes. And that way, you don't have the shared memory infrastructure. You know that any mutex is held by that it's not got mutexes that you're worried about. Whereas if you kill a thread and it holds a mutex, there's no guarantee what state the data that was locked, it was protecting was, whether or not the OS is necessarily going to allow somebody else to get the mutex lock, and all sorts of things like that. So hard killing of a malfunctioning thread is a bad idea. If your system needs to do that sort of thing, I would say use processes rather than threads. And yeah, so I think that comes to the end of the questions that are actually there at the moment. If anybody has anything else. So a new question's come up: recommended architectures for graph-based tasks. So yes, so I'm thinking in terms of you have an initial task that then spawns some subsets of tasks that then the data from each of those. So we've got some form of pipeline infrastructure that that you can pass data through, whether it's just the once or in the series. I think if you've got a system that allows continuations, then that works really well. There's a lot of discussion with the standardization committee at the moment for ways of building such a pipeline that looks easy to use, and the standard ranges sort of structure seems to work quite well, certainly, but obviously that's primarily within a single thread. But there are quite a few pipelining style application libraries that you can use for building stuff and things like that. But I certainly haven't got a short and pithy answer for recommended architectures. I'm not currently planning on a C++20 edition of my book. The C++17 edition also covers lots of the things that are in the concurrency TS. The new additions to C++20 are largely essentially discussed already. The big thing that's missing is, well, there's semaphores are not covered, but semaphores really are quite low level. and using using them correctly, you're probably going to want to look outside of what I would have talked about anyway. And then, of course, coroutines, but actually with C++ 20, coroutines themselves is just a pure infrastructure. There's no library there. So I don't feel that there's too much missing from C++ 20, from the C++ 17 edition that you would have wanted in the cover for C++ 20. So hopefully everything in there is still valid. And how does overhead of coroutines compare with async and future and job queue? Well, that really, really depends on the coroutine library. If you, in the extreme case, the coroutine library can have no overhead, potentially even what amounts to negative overhead, because the compiler can inline things and eliminate some shared some overhead that would have been shared. On the other hand, if your coroutine library has been designed in a less ideal fashion, and has got lots and lots of memory allocation and locking overhead, then that might end up being quite a lot more overhead than would be comparable asyncs and futures. So at the moment, then, I'm not sure that there's any really bulletproof coroutine libraries that I can look at and say, yes, well, if you use library XYZ, then I know what the overhead is going to be and how that compares. But really, it does depend on how you write your library. Obviously, if you write it yourself, which is a strong contender at the moment, then you're in full control and you can see quite where all the overhead lies. But be warned that if you try and do that, it is hard. It is a non-trivial task writing a proper coroutine library for multi-threading. Okay, so I'm going to stop taking questions here now, and I'm going to move to just the tables in Remo. So I'm going to sit on floor 8 in the embedded room and see if anyone's got any questions.